Introduce our speaker for this session, Mr. S.K. Chong, co-founder and security consultant, Scan Associates and Jan Berhad. SK is co-founder and security consultant of Scan Associates. Hacking into banks, ISP, military, and government sectors is part of his job. He wrote a few security white papers on how to break network with SQL injection, buffer overflow, shellcode and stuff, including one of which published in Frac eZine number 62. His presentation was heard in Black Hat Singapore 2003, RuxCon 2004 Australia, and XCon 2004 China. He enjoys playing Capture the Flag game and was in a team that won several CTF games from Hack in the Box 2002 and Black Hat Asia 2003. Join me in welcoming Mr. S.K. Chong, who is going to present his paper, Windows Local Kernel Exploitation.
So this will be the last sessions of the entire conference. So we're going to do this thing quickly so that everyone can go home. All right. The title of my presentation today, Windows Local Kernel Exploitations, was presented in XCons last 2 weeks. Immediately after my presentations, I received some comments and stuff like that. A more appropriate title could be exploiting the kernel LAN using device driver communication problem. I thought that would be a very long title, so I shortened the things. It's going to be Windows Local Kernel Exploitation instead. Will everyone hear me okay? Okay, the back there, is it clear? Okay, so we're going to start right ahead. So the overview of my presentation, first we're going to look into some of the previous known attacks on Windows, in the Windows world about privilege escalations. That will include some of the LPC problem, exploiting system applications and stuff like that. And then we'll move into the main things that we would like to discuss, the Windows kernel itself. Before we can move into exploiting some of the stuff inside the kernel, we have to have some fundamentals understanding about Windows kernel. That will be covered in the Kernels 101. And then we look into the actual problem that we'll be exploiting today, the device driver communication problem. We'll look into the most important API that we need to use in order to carry out this attack, the device I/O control API. And then we'll look into some of the mechanisms that we demonstrate on how we can find this kind of vulnerabilities on our own in the finding sections. And finally, the mechanism on how we can exploit this particular problem in Windows world. Once we know how to find and how to exploit the probably, so we still have a bit of problem that we need to figure out. That's include writing up kernel shellcode. Although it's not widely popular, but there are actually some materials about writing Windows kernel shellcodes, and we're going to look into how we can do that in kernel shellcode. And finally, a way to make our exploit more stable by using some of the undocumented IPR in Windows. Okay, local exploit should be stable. Okay, it should be run because otherwise it won't make sense to have a local exploit. So we want to make our exploit stable. So by using some of the undocumented API, precisely into the anti-query system information. This is a very useful API, and we can use this API without any privilege. Even a guest or IUSR from IIS can actually use this API. And we do a bit of demo after that, the end of the presentation. Okay? All right. So, flashback about what has been done in the past about Windows privilege escalation. It's not a very popular technique because most of the exploit or vulnerabilities you find in Windows, a simple shellcode like revert API will actually gain you back to a system. So most of the time, if you're exploiting some kind of a buffer overflow in Windows, you will automatically be granted a system privilege. That's why Windows privilege escalation has not been a very popular topic. There isn't that much need, okay? But in some case, we found during our pen test, we actually need, we need some privilege escalations, especially when we break into one of the systems using ASP secure injections, maybe web problem usually, which actually grant you just RUSR. That's why the research started once we have the need into looking into this privilege escalation problem. So previously we have like the most famous things is like exploiting system privilege applications in Windows. Now, as you know, there are many system services running in your Windows, and exploiting any one of these system services will probably grant you a system privilege. One of the first one probably will be the buffer overflow in still image. This one was discovered back in year 2000. I think DuDoc discovered this bug. It's a buffer overflow, and after that there is a server-side include .dll. This is DLL has been used by IIS, so this one has been found by NS Focus, I believe. So it's like if you can upload an ASP file, certain tag inside the ASP file can make your IIS crash, and will gain you a system privilege. And there is the very famous IIS IDQ.dll privilege escalation using some specific name in your file will make Windows use a different set of mechanism to process your credential, which if you like things like HTTP, ODBC.dll and IDQ.dll, a simple revert to self will grant you a system privilege as well. And there's also recently there's a buffer overflow in POSIX subsystems of the Windows, which also will grant you a system services. But these are old news, so they are exploited and has been exploited. This type of thing. So, but all of these type of attack require a system services. So as long as you can attack one of the system services of Windows, you will grant a system privilege. System privilege is like one of the highest privilege available in Windows. And other than the system privilege applications, there are also a lot of LPC problem, mostly been discovered. I think all of them actually been discovered by Todd Sabin for Razer team. So we look into roughly what is the local procedure call problems later on. There's also a name pipe impersonations problem. There's also shatter attack, and finally there is also kernel bugs. Okay, kernel bugs will be which we are interested today. Okay. So first we will skip the system privilege application because it's mostly relevant to the application you are attacking. So okay, there's no general things that we can talk about here. But the LPC problems like the local procedure call, one type of privilege escalation, mostly researched by Todd Sabin. LPCs actually allow processes to communicate between each other in a single computer. So this Razer team guy, he actually discovered various problems, including how do you impersonate your LPC port as the other so that the server can allow your communications. He actually, I don't know, maybe reverse engineer most part of the things. He figured out that some message ID and port and things like that, if it is in a specific number, will allow your server to accept your communications. So you can get the details from many of their advisories. And there's also actually silence problem in one of the NTLM security provider LPC port, which you can find the relevant advisory in the link over here. Okay, but the last one, silence problem, only available for Windows NT. You can only attack Windows NT though. So there's LPC problem, there is name pipe impersonations. This is interesting. A server name pipe can actually impersonate its client. A name pipe is like also a mean for communication between two processes. So you can actually create a name pipe so that anything you send to that name pipe will eventually reach your client program. So they have these features in Microsoft which allow a server to impersonate its client. That is for good use, of course, but actually the attack can be carried out in such a way that the attack attacker will create the name pipe first before the server has a chance to create it. So if you know some popular system services that create specific name pipe like ABC, for example, all you need to do is just create the name pipe ABC first before the server create that. So whenever there is a privileged client trying to connect to your pipe ABC, you will be able to impersonate his privilege. So we will be looking for client that is connecting from a system privilege, of course. So by just creating a pipe before the server, we will be able to get our privilege into the system privilege. And there is a very detailed paper call written by Breakwatts and Shaw, okay, in the link over here. Maybe you all can refer. This is also not what we will be talking about in this presentation. So we will quickly go through the last type of privilege escalation problems known as shatter attack. This has been quite popular recently. It's actually utilizing the window messaging systems. So window message allow any application to send any message to another applications. Okay, the basic shatter attack required you to locate a privileged window in your desktop. Okay, locate the privileged window handler and then send in the shellcode to that process. The shellcode in this case can be just a normal string. It can be anything. So as long as you can send one message to the target process, that particular message contain things that you want the server, the service to execute. Send it over using in a text box using any other message API, and then send in the WM timer message to the target process. Now this message will actually make the server execute something like a timer, okay, to execute something on certain a time. So when the time elapses, so you can point it to jump to the shellcode you have previously sent to that process. Now this is like you send in the shellcode and then you ask the server program to run your shellcode. In nutshell, it's going to be just something like that. So when it also means that you can arbitrarily insert any kind of shellcode you want the server to execute. It's kind of fun and it's worked just nicely. But actually, other than W timer, there are other type of API that you can use, which has been documented in many other advanced shatter attack. Okay, but unfortunately, this type of attack require a desktop object, meaning most probably you can only perform this type of attack if you are in front of a computer. So if you have access to the desktop or if you have the terminal service, so you need the desktop in order to carry out this attack. As I've been talking to Brett Moore in Ruxcon back then, he actually presented his paper on the shatter attack, shoot the messenger in Black Hat as well. This is mostly known as local attack, and is that you have to be local in front of the computer to carry out this attack. So we find this thing have limited use in our pen test. So we need to find other type of mechanism to exploit to do a privilege escalation. There we go into the kernel bugs. So these things has been gaining popularity. It's exploiting problem that exists in the kernel LAN itself, the Windows kernel LAN. It should give us the highest access, same level of access of the operating system. Okay, but unfortunately the Windows kernel is not a very well documented area. Okay, it's generally more complex than the user LAN. So most and there hasn't been many exploit about Windows kernel yet. Okay, and because it's more complex, the kernel is more complex, less documentation. There's still probably a lot of chance for you to find some bugs of your own. So I say there will be probably still plenty of fish. Fish is a term that's Fred Harwood would like to use in order to replace bug. Bug is not interesting. Fish is interesting. A bug might not be exploitable, but fish probably more interesting, I say. Okay, it's gaining popularity, as you can see on the next slide. These are some of the kernel LAN related problems being found by security researchers around the world. One of the first one also was discovered by NS Focus. Those Chinese hackers, so closely related to the X Focus. There the MPU driver, of the Windows kernel have buffer overflow on some requests. You can get the details from the advisory. There is also XP redirected buffer overflow, okay, which is like you can just carry out this attack with net use and with a very long share name 64K. Net use is a simple command for you to just share something, use a share on a different machine, on another machine. But just use net use and a very long name 64K. You can cause an overflow on a Windows XP. Of course, this has been fixed. All these bugs over here has been fixed, and there is the third one over here. Buffer overrun in the Windows kernel. It is on the debug information. So there's also a buffer overflow in the debug information written by the kernel. There is also most recently 2 more bugs discovered by EI. The virtual machines VDM TIB problem. There's also expand down data segment problem. Both of these are very complicated. I still have not been able to create an exploit out of this yet. But it looked like from the advisory this is interesting. Okay, from EI. And finally, other than kernel bugs, there is also a device driver communication problem. There is a very detailed paper written over here. I would advise you all to check this paper out. And in fact, most of the research that we will be talking later on in my next presentation will be based on this paper. And I have only managed to improve a little bit from this paper. So if you got a chance, you should try to look into this paper. We will look into what exactly the device driver communication problem is, how to exploit it, as well as like a demo on how this thing really works. Okay. So we are moving into the Windows kernel 101. So I think we can be interactive in these sessions, although like I'm very far, and with mic and all. But feel free to like interrupt me if you have questions before we move on. Okay, kernels 101. So kernel Windows operating system divided into 2 main areas, the user LAN and the kernel LAN. This is much like in Linux as well and BSD, where you're going to have ring 0 and ring 3. Okay, this is more like actually this is Intel architectures. Ring 0 indicates the highest privilege area where you can have full control of the machine. You can access some CPU register which is not available in other ring. Whereas in user LAN, if you have ring 3, this is the outermost ring, which is like the most confined, contained environment. You only have limited amount of CPU instruction where you can execute. You can only process a certain range of memory. So it's like contained area. This is where most of the user will see the desktop and everything. They are executing in user LAN. Okay, and the user LAN in user LAN, Windows user LAN, each process will have 2 GB of memory. Okay, the memory range from 0 until 7F onwards. Okay, 0 until the first 1 gig. So each process will have its own distinct memory address. So anything you do on when you started the program, anything you do on that process will only affect your own process. You will not be able to interfere with another process. And it's like more like a sandbox over here. You cannot actually crash your programs, supposedly, if the thing's correctly been implemented. It's in a controlled environment that is in the user LAN. Whereas in kernel LAN, everything will be more interesting. Once you are in the kernel, the kernel LAN consists of the actual kernel itself and some device driver. They all are sharing the same 2 GB of RAM memory, and the memory address is starting from these 8000 onwards until 2 gig. Okay, and basically once you are in the kernel, you are in ring 0, you will be able to execute anything, including controlling the user LAN and things like that. So basic point to remember, there are 2 distinct memory range, the user LAN and the kernel LAN. Okay, then as I mentioned earlier, the kernel LAN consists of the actual Windows kernel itself, NTOS, the NTOS, the EXE, and some executive processes, like you must have processes that manager that handle all the process and thread. You're going to have the IO manager. This is interesting. We'll look into more of this. You're going to also, only in Windows, you can find the user GDI, which is also happen to be in the kernel. Very big chunk of memory occupied in user kernel for user interface. And you also going to have all bunch of device driver. All of these things are in the kernel land. What is more important is that the Windows kernel itself contains many important structures which known as the executive objects that control the behavior of application in the user land. So if you can manipulate this object in the kernel land, you can shape the behavior of the application in the user land. One important part of the kernel is the device driver. It is equivalent to the loadable kernel modules in Linux. It is something which execute at the same privilege as the kernel, but the user can actually create their own device driver to run these things on the same privilege with the OS. It's the only mechanism in Windows where you can create something equivalent to LKM. Once you have created a device driver running in the kernel, you will have the ability, as I mentioned, to change the behavior of the application in the user land. And in fact, this has been the features that been preferred by many vendors, including antivirus and maybe antivirus, and maybe some of the personal firewall. They're actually using this particular device driver to control your user land. For example, antivirus would like to check every file access. So whenever there's new file you are trying to write over to the hard disk, he need to check that as well. So by introducing a new device driver in the kernel land, antivirus can intercept all read and write access of your hard disk, for example, and maybe check for viruses and stuff. Personal firewall might use device driver to control all the network connections as well. Okay, it's easier if you have a device driver running same equivalent privilege with the kernel. You can check almost everything. Okay, now. This is the things that we would like to attack, the device driver inside the kernel land, because attacking one of these device driver will eventually give us a privilege of the operating system itself. So before we move into attacking it, we like to know how the device driver communicate with the user land process. There are actually 3 API that a user land can actually call in order to communicate with a device driver in the kernel land. A user land process can actually use read or write file API, or he can actually use device IO control API to send some data or to receive data from device driver in the kernel land. Before you can use any of the device driver, you need to use a create file to open up the driver for communications. Once you have created a file, a device driver created, you just create a file to create an object of the device driver. You can use that object pretty much like a file system using read or write or even device IO control. This is the basic mechanism on how a user land process can communicate with a device driver in the kernel land. Now, the basic flow of the data will be like in your user API, you probably will execute device IO control, read file, write file, and things like that, and then it will turn into your the internal API, maybe an NTDR, maybe NTOS. You're gonna have the NTXXX, maybe NT device IO control file, right? So data you pass over to before you can reach the final device driver have to go through the internal API, and from internal API you have to go through the IO manager. This thing has been implemented in NTOS, and you have to go through one of the most important functions, IOPXXX control file. Now, this is the real name of the functions in IO manager. You can obtain this name by installing the debug information and trace the things using soft eyes. Now, the IO manager over here has the responsibilities of checking the user land pointer and things like that. So most of the problem should be solved over here. If things been solved here, we probably will not be able to exploit anything. But we will see why we still can probably go through sometimes to bypass this I/O manager. So once he finished with the device I/O manager, the final request will eventually end up in your device driver, and the device driver will have a function called driver dispatcher that actually handle the communications. Okay. So a basic device driver skeleton is similar to something like this. You're going to have the driver entry. The entry is the initial process that your driver must execute when your driver starts. And then you're going to have the dispatcher. As I mentioned earlier, this will be the main function in your driver that process the user request. And you're going to have driver unload, of course, if you want to unload the driver. So the most important things over here will be data from device I/O control will eventually end up being processed in driver dispatcher. Okay. So since we're going to be using this device I/O control a lot, so remember that our final objective is to obtain like a previous escalation, and the most important API we need to remember will be this device I/O control. It allows communication between user LAN and kernel LAN, and basically any user program can send some control code using device I/O control to any device driver. Okay, in nutshell. Okay, what you need to do is after you send it, you probably will receive some output from the device driver, and the output will be from this device I/O control. And the device driver will return the output to user LAN via the output pointer specified by the caller. Perhaps it's clearer if you take a look at this. This is the API header for the device I/O. It will only return true or false, and we need to specify the driver we need to communicate with, and this will be the control code, the actual code that the driver must understand and process, and then you're going to have the input buffer, the data we want to send over to the kernel, the length of the input buffer, and you're going to have the output buffer, you're going to have the output buffer size, and whether you're going to be overlap and how many bytes returned. This will be the number of bytes returned will be from the device driver as well. Now the interesting things about this API is that what if you might want to ask you, what if you specify a pointer over here that belongs to the kernel? Okay, that belongs to the kernel. Will the return value returned by the device driver override value inside the kernel? So basically, the next slide is some of the things that we should be we should be thinking. What if the output pointer is a memory address in the kernel? Will we be able to override anything in the kernel? Because by default, a user LAN will not be able to access anything above 8000 onwards, because those memory range belongs to the kernel. We cannot change anything over there. But if you can use a device driver which is in the kernel LAN to help us to manipulate this data, we probably can override some 4 bytes of information in the kernel. So by actually taking advantage of this, what if we override like important function pointer in the kernel, or what if we override some important tokens or structures in the kernel executive objects? Okay. Now, unfortunately, the I/O manager actually provide buffer handling for device driver. So basically, the device I/O manager, the I/O manager will try to check your output. If your output is in the user range memory, you will be able to process and things like that. Okay, so I/O manager actually hinder most of the problem, but we have to look into what specifically the I/O manager is doing. What we have discovered from searching mostly the OSR website, which contain a lot of information about how to write a proper device driver, we encountered that the I/O manager actually provide 4 type of communications buffering for device driver. So the first type, method 0, the I/O manager will automatically allocate its own buffer, non-pool buffer, from the automatic locate its own buffer, and it will copy the user LAN data into its own buffer before he passes this data to the device driver. So this is very cool. I mean, it's safe because before he actually copy this thing, he performed a write pop check and read pop check. So, okay, actually pop write check, and he actually performed all kind of checking. So if we discover any device driver that is actually using method 0, it's probably safe because the I/O manager handles the buffer management. There is also another type of I/O manager method 1 or 2, which is the direct I/O. This is mostly used in DMA, direct memory access. You know, I think back a couple of years they started shipping hard disks with DMA access and things like that, direct memory access. Those are for fast I/O processing. In this process, the I/O manager will actually log in he actually will create an MDL, memory descriptor table, to map the virtual memory into the physical memory, and then he locked the physical memory and passed the physical memory to the device driver. So the device driver will process information only using the physical memory. I found that this method 1 and 2 also pretty safe, so there's not much thing we can do about it. But the last one, I/O manager actually provide the third mechanism of buffer management, which is neither I/O, meaning that the buffer management will just simply pass the pointer from a user LAN to the device driver. So it will not process anything, it will not probe for anything at all. So this is the one that is most interesting. If we can find some device I/O API that uses neither I/O method 3, we can potentially exploit this type of vulnerabilities in order for us to create an arbitrary write of 4 bytes or maybe sometime more on the kernel LAN. Okay. Now, if you check into the header file of the NTDLL, I think it's on the NTDL or one of the DDK. The device driver development kit from Windows, CTL code, actually the code that you're sending over to the device driver can be constructed using this macro. So the first 16-bit it's actually the device type you're communicating, and then there's 2 more bits for access, whether read or write, and there's 12 more bits. This is supposed to be the user-defined area where you specify what you would like the device driver to perform. And the last 2 bits is the method we are talking about. So if it is 0, 0, we know that it is buffer I/O, okay, because it's method 0. If it is 0, 1, we know that it's probably a DMA, okay. Now basically, to sum up these things, whenever you receive a device I/O control that ends with a binary 1, 1, which is equivalent to 3, so it is probably using a neither I/O communications, meaning that I/O manager will not try to probe for the memory. He will just send the pointer to the device driver. So whenever you detected an I/O control in device I/O control API that ends with 3, 7, B or F, this type of device control code actually uses the neither I/O. Okay, so in this case, it is possible that the output pointer can be anywhere in the memory range. Now we are talking about the whole memory range, even the kernel memory range, starting from 80 or onwards, and it might allow arbitrary memory write. This is what we want. Once we can achieve this, we can probably exploit this. Now, how do we find this side of neither I/O control? So you can actually refer to source code or header files. If you have in terms of open source projects, you probably will have the source code of the application you are auditing. You probably can check the source code, or you can check the header files of the platform SDK. So let's take a look at if you install Visual C++ and things like that, or you can actually it will actually install the platform SDK on your machine, and inside the platform SDK contain bunch of header files. By checking into the header files, you probably can tell whether what the device I/O is using a neither I/O. So okay, Visual Studio.NET. you should see platform SDK. So include files over here probably will contain some of the NIDER IO things. So if you quickly do a search over here, file string, okay, file string, I would like to look for all the subdirectory NIDER. Okay, all the header files. So as you can see, the word NIDER over here, now CTL control code. So in available in ks.h. Now it defines this particular IO control code uses or the kernel stream, and it actually uses the NIDER IO device IO communication. So meaning that any process that want to use the kernel stream, in this case that uses this IO control KS property, is probably using a NIDER IO device driver communication, meaning the IO manager will not check the pointer. Okay, so in fact, if you continue searching, not only the kernel stream uses this, there's also Win IO control. This is the definition, which is 3. Okay, you also see that most of the FS, the file system, NTFS system, also uses NIDER IO for communication with the device driver in the kernel. So method IO. So all this IO control code over here is not using IO manager. So if you can like send in one of these API, it is possible that you can specify your own output buffer into anywhere, including in the kernel land. But to be frank, I have checked most of these things, including most of the NTFS file system. If you check into NTFS SYS, the sys file in the sys32 device, discuss the thing into using your IDA, you see that even though the IO manager is not checking the output buffer, the NTFS .sys itself actually perform the checking. So I would say, I didn't check most of them, but I would say most of the NTFS over here, although it is using NIDER IO, it is not exploitable. Okay, I cannot tell for sure whether the kernel stream is exploitable. This is mainly used for the multimedia communication things. I haven't looked into that properly, but this is one way where you can try to find NIDER IO control code. So if you have source code like there's another thing, like if you have source code of which I'm going to show in a slide. For some of the open source project, you can also find it through the source code. Okay, that is looking into header files and source code. Another mechanism where you can use to find NIDER IO is to use cool tools like strace -p PID or just strace. If you application hooking to find all the device IO control API. Okay, look for all the device IO control API. You will find some of them actually uses NIDER IO. We will demonstrate one of them later on. Also, you can use a system-wide hook like a tools presented in undocumented Windows 2000 secrets, Win2K hook, and try to search for all the API access, internal API access to device IO control. You probably will find anti-device IO control file and things like that, which process this type of API. So by examining the parameter in this type of API, you will find some of them actually uses NIDER IO. Now, for an example, okay, I try to give an example of some of the mechanism I presented just now. Looking into source code, okay, by checking the source code of the WinPCAP, even to the latest version right now, you will find that, this bug was actually discovered by Metaslug, a member in Xfocus. No, he's not really a member, but he's closely related to Xfocus guy. He released this advisory in Xfocus. There is a NIDER IO which he can found by the source, like define IO control code as 9031. If you convert this number into a hex number, it's gonna be like 2347. If you remember, those that end with B, 3 or 7, they are using NIDA IO. In this case, this one is definitely exploitable. We can confirm on that. And in fact, if you look into the packet header of the WinPCAP, WinPCAP has been used by many products. In fact, if you have Etherview running on your computer, you probably have installed WinPCAP. All right. In this vulnerable. Now, by looking into the packet header of the WinPCAP source code, you find that there is other potential IO control code which is vulnerable. 1CF3 is vulnerable. 1CF7 is vulnerable. Now, if you take a look at the packet header, you see that the writer are simply defining the IO control code in sequence. It's like 7411, 7412, 7413, without much understanding that this thing actually, in fact, affect the buffer management. Okay, he will just create the IO code, like increase the things. So he released some proof of concept in Xfocus, which you can try. Okay, for privilege escalation. Okay. So this is another sample output for finding NIDA IO via the system hook. Using Win2K hook applications, we try to capture all the API access to device IO control, and we will see that if you have Norton antivirus running, you're gonna have like, okay, and the VIP is running, and then he's calling anti-device IO file API, and this is the list of parameters that he uses, that the process uses, and one of the parameters over here, N222A87, is the device IO control code. As you can see, it's end with 7, so it is also uses NIDA IO, and this is definitely exploitable. We will demonstrate later on. Not only that, you will find some other things like device TCP, device driver in this is mostly in XP. N1200 integer 3. This is probably also exploitable. No, I mean this is using NIDA IO, but in fact this NIDA IO is the one that has been used by the XP to be specific. If it is in Windows 2000, when you type netstart, you will see the list of connection. Yeah, but if it is an XP, if you type netstart minus N, A, O, the O parameters, you can even see the list of port open. So this is an extension of the TCP/IP available only in XP. So it's been used extensively in XP. Okay, these things, but I haven't found whether the things is exploitable. You may try in the device TCP device driver. And there are other similar things if you just perform a system-wide hook to look for device IO control. So, but yeah, this is also using NIDA IO, but this will be not exploitable, say, because the output pointer is null and the output length is null. So meaning that it will not return anything in this case. So this is probably not interesting, although it is using NIDA IO. Okay, you can just run it on your system. You can get this thing from the Insight 2000 website. This file, these utilities. Okay, we will move into trying to exploit one of the sample of the vulnerable applications that uses the NIDA IO. So I've been saying that we try to look for it, but once you've found it, how do you know whether the thing is vulnerable, and how do you exploit in order for you to gain privilege escalation? So I'm taking an example of this Norton Antivirus Enterprise, which our company uses. So unfortunately we purchased these. So I got a chance to test this thing out. So I traced the soft files back until where we found the antivip.sys device driver, and then it actually uses device IO control. If you disassembly the antivpa.sys, you see the list of control code in this device driver. It's similar to this. He uses all this control code. A83 is one of them. A87 is another one. So as you can see, all of them end with 3, 7, B, B, F, 3, all of them uses neither I/O control code. So Norton Antivirus actually uses this heavily. Maybe it's for the performance, but what they didn't take into consideration when you're using neither I/O, user can actually exploit this thing to override arbitrary memory in the kernel. And this is precisely what we're going to do. So now, if we have called the device I/O control and we specify the output pointer to a memory address in the kernel, so we will be able to override 4 bytes in the kernel. What can we do? What if we override the return address? It will be similar to a classic buffer overflow. When the process returns, it will jump to our shellcode. So we gain the ability to execute anything. If we override a function pointer, whenever the next time somebody calls that function, it will also jump to our shellcode. This is like double free, or maybe some other maybe format strings. Okay, and we also can probably override a switch jump table, which I'm going to demonstrate with the why is it more useful in this case. Or we also probably can override service descriptor table. This service descriptor table is the one that holds the list of interrupt 2E, where the system handle. I mean, if you look into some of the rootkit source code, you probably will have better idea. Service descriptor table. Or if you have been to Chiu Kyung's presentation yesterday about how to capture kernel rootkits, this you probably will get more understanding about service descriptor table. So we need to override a memory area where it will be accessed by another kernel process later on. Once you have overwritten that value, whenever the kernel try to jump to access that memory address, it will jump to our shellcode. So we can basically execute anything on the kernel level at that moment. Okay, so the pseudo exploitations. So I would like to sum this thing up. Okay, it will be similar to you call the device I/O control. This is the attack. So of course, in the end of the attack, you're going to have a binary where you can just run to do the escalation. But if you want to write the things yourself, this will be like the basic mechanism is to call the device I/O, okay, and try to get the output return from this device I/O. The output is important, okay. And then we will allocate the memory address in our own user land of our program. We try to make it executable and read-write, and then we copy our shellcode into that memory range. Then we will create the file to access the driver, send in the first signal, device I/O control, with the vulnerable I/O code. Okay, and more importantly, we supply the out buffer somewhere in the kernel where we want it to override. And so this first signal will actually override some part of the kernel, and we send in the second signal, in this case, to cause the device driver to jump into our shellcode. So at this moment, the shellcode will execute whatever we put in the shellcode will execute. Okay. Now I mentioned that we can actually override a function pointer or like service descriptor table. We can the easiest way to achieve achieve executions is to override the switch jump table. So why is it easier? Because most of the device driver, as I mentioned in the beginning of my presentation, device driver usually have 3 main important functions: the driver entry, okay, and the driver dispatcher, and the driver unload. In driver dispatcher, as you can see, this is a sample source code of driver dispatcher. He will try to check what type of I/O control he received, and then he performed the things in a switch case statements. Okay, you're going to find a lot of switch case statements in most of the device driver. So how do once you compile this switch case in C, how does it look like in a memory? If you disassembly this thing, it will look similar to this. The compiler actually create a switch jump table. Okay, the table over here actually contain all the offset to the the location of the depending on the case is processing. So if we can override this jump table, so say if we override the first one over here, this pointer, instead of jumping to the case 0, if we can override this thing to point to our shellcode, the next time when this program runs, when you try to jump to case 0, it will actually jump into our shellcode. Okay, so this is precisely what we want to do. Okay, so now that we have like we know where we want to override. I already basically explained this. Okay, we were trying to override the first case. Okay, try to override the first case. When the driver process the case 0, it will jump into a shellcode. However, we still have one little problem here. Now, in the case of device I/O control, the driver will return whatever value the driver wants. So in this case, we can override arbitrary memory, but we cannot control what value the driver want to put into it. So basically, we don't know what the driver want to override the memory address with. So in this case, if you're exploiting this Norton antivirus, you see that that value of memory actually will be overwritten with 4. It's always consistently. So if we point this thing to the memory range of 8,000, so after the first device I/O signal, the address 8,000 will be overwritten with 4. We cannot control this 4 value. It's something returned by the driver. So this is our problem. How do we exploit this thing? Now, because it's always return 4, override with 4. If we override case 0 with 4, this is case 0. Now this is your memory range of the jump table. If we override case 0 with 4, and we cause a jump to case 4, it will try to jump into 004. But this is not a valid user range. Although it is in user length, but you cannot allocate memory in pitch 0 because it's been designed by Windows to capture exceptions. Okay, you cannot allocate memory in 0 over here. So what we do, we will try to override instead the middle of the second case. In this case, we are not overriding here. Okay, we will override here. Why do we do that? Because if we override here, now remember, Intel is like the little Indian things were like the other way around. So like this is actually the value 4 in this sequence. So if we override here, we actually override part of the case 1. As you can see, we didn't actually disturb any value here, but in this case, once we start override here 4 byte, okay, we will override partial of the case 1. Now in this case, the next time if someone jump into case 1, okay, the memory address will be we only change 2 byte of the case 1. Perhaps it's clear if I show the next slide. So if we override here, now if we trigger case 1, it will jump into 0004XX. We didn't actually change these 2 numbers. Now if we override 2 bytes, case 1 will become this memory range. Now we can actually allocate memory in this memory range. So that is why before we trigger the case, we allocate our memory over here in the 0004 and copy our shellcode into it. So then only we cause the override, and we call the second device I/O control to cause the case 1, and when it's case 1 happen, he will jump into our shellcode. Okay, all right. So this is not like the buffer overflow, whatever. We just have the arbitrary memory right, so it's easier. Okay, now. As I mentioned earlier, so device driver will jump into 0004 XXX after the second signal, and then we have to allocate this memory range before we call the jump. Okay, and we need to copy our shellcode into that memory range. Now, what do we need to write in the kernel shellcode? Now, kernel shellcode is different from the ordinary user shellcode. You are operating at the device driver level right now, okay? Operating. So using socket and all will be very difficult, and you will make your shellcode very big. And in fact, most of the research has been carried out by a friend of mine from ex-workers, IAS. He actually proposed to use a very elegant, simple shellcode. just to change the privilege by manipulating the Windows token. So you can find his paper in this link, where he's trying to exploit the local kernel's overflow in the debug message. Now the technique that he uses will be, he first will try to locate the system token, and then he will just need to replace the current process token with the system token. Now what precisely is this token? Okay, Windows actually identify a process based on these tokens. So if you have system tokens, Windows will think that you are a system process. So anyone that have the ability to change your own tokens to point to a system tokens, you will be able to emulate as a system. But the structure which contain the pointer to these tokens is in the kernel land. So if you are a user process, no way that you can change this. But now that we are running as a device driver, we will be able to change this information. So the first process into finding the system, finding system token, we need to find the system process first. Okay, we need to find the system process. Now we need to locate the E-thread. E-thread is one of the structure inside the kernel mode by locating FS124. Okay, this register over here with relative 124 will always point to the current E-thread, the current E-thread. So from E-thread we'll jump into E-process, because E-thread contain one of the pointer to E-process. From E-process we use one of the members active process link to loop into all available process. So using this technique we will be able to loop into all running process. Okay, this is similar tricks like what they do in rootkit as well. Now for each process we will check one of the few unique process ID to compare if it is 8 or 0, 8 or 4. System PID of 8 indicates it is a system. In XP it will be 4. So if you see from your text manager, okay, a PID of 4, this is a Windows XP 2000, Windows XP Service Pack 2. System service always have PID of 4. This is fixed for all the XP, and it will always have 8 for all the Windows 2000. So if we can locate this, we will be able to find the system process. Okay, so we can use a similar technique to find any other PID. Now basically what to sum up with, it will be similar to this. You use the FS124 memory address to point to the E-thread. So within E-thread, the first member of E-thread is actually the K-thread. So one of the members in K-thread is actually KABC state, and one of the member in KABC state is the E process. Okay, E process actually, which is precisely, it's fixed in 2000 and XP. 44 will be the offset from the initial E-thread, will allow you to point to the E process. Among other important things in E process field will be the active process link. Active process link will have a forward link and a backward link. It's a double link list, which allow you to loop forward or backward for all the process. You remember you are in the kernel right now, so like you can actually jump into all the available process. And then inside the E process, you also will have the inside active process link, you also will have the token pointed to a token. Okay, you also will have unique process ID. All these are important information to us. So the basic idea is, once you are in E process, you will read the first forward link. Okay, the first forward link will allow you to jump to the next process. So the next E process will, and then you compare the unique process ID. If it is equivalent to 8, you know that this is system. Or if it is XP, you check this whether this thing is equivalent to 4. Okay, you continue to loop over here until you find the unique process ID equivalent to 8. Okay, so once you found unique process ID equal to 8, you will manipulate the tokens. Okay, now a little bit more about how that we can escalate into our system. The Windows Security Reference Monitor, okay, this has been defined inside Windows 2000, a very good book, the third edition. He will identify every process uses based on the tokens. To become a system, we just need to get a system token. So the easiest way to do this is, once we have located the system process, we change our process token to point to, because it's a pointer, we just need to change it to point to the system token. So it will be similar to this. So we found we have two processes. This is our own process. Okay, we probably were going to have a guest token, limited privilege. This is the system token. System token will have a pointer to the system token. System process will have a pointer to the system token. Now all you need to do is just to swap this thing, change your own pointer to point to a system token. Now just by changing one pointers over here, it will automatically change your process into a system process. So okay, it's as simple as that. Okay, the code to do these things is just like 20 character longs of after in bytecode. It's very short. Okay, so that is like we already can escalate any process into system. So among other things that we need to do is to make our device driver more stable. So in this case, we need to override exactly on the. We need to override the switch jump table. We need the exact location of the switch jump table. And what we have discovered is the base address of most of the device driver may change from time to time. As I mentioned, all the device driver actually sharing the same 2 gig of RAM memory. So if like any change of sequence of loading, or maybe you introduce a new device driver, the base memory for the device driver we are exploiting will change. So if I can create an exploit, it might not run on your computer. It will crash on your computer. This is not good. I don't want that, and I don't want you to like go through the process of writing the exploit and all. So I want to create an exploit which will work in most of the time. So we need to capture the base address of a device driver. Now, fortunately, we discovered there is an anti-query system information API in Windows. This has been widely exploited in some of in serious programming. We probably will need to use like PS list and all. They actually uses anti-query system information to obtain the list of processors and stuff like that directly from the system. Now, one of the important structures that you can obtain from this API will be the system module information. Inside the system module information, you can get the list of base address of all the device driver. The output will be similar to like maybe this P state. So now, as you can see over here, the list of modules running, okay, and TRS, the base address is over here. You see that most of these address are above 80 because they are in the kernel LAN, right? But this is the pstate command. But pstate, you will not be able to run pstate if you are not admin. So I think so. That's why I create my own API to obtain this information. Okay, so so the one that we would like to exploit will be the Norton antivirus. So I haven't started the Norton antivirus. Maybe it's time to start it now. Oh, but I think the driver is loaded. Okay. Okay, anyway, you get the base address here, but what we need to do is like we do not want to rely on any other things, so we use the anti-query system, which you can execute even if you have minimum privilege, to get the base address of our device driver, and then we calculate the relative address from the base address to corrupt the jump table. Okay, so other than that, I would like to introduce a features which allow me to execute, to escalate any other process. I don't want him to escalate only my process, because I find that when I get into a Windows server, I got a ASP shell. I will be only running as the IUSR or IWAM user. So I want to escalate DLL host. That's why I created this another functionalities which allow me to escalate any process. Basically, I'm using still the same API, anti-query system information. This is previously undocumented and used to obtain the system process and thread information. Okay, which allow me to get all the process name and ID. So with the process ID, remember I already can use the small routine I wrote just in ASP script, which allow us to execute system command on the web server. So if you can upload ASP on a Windows Windows machine, you probably can execute command. Okay, so but the thing is, Norton Antivirus will try to detect this, and it will report this as a backdoor. So apparently, so when I discovered that, I use a Microsoft script encoder technology from Microsoft themselves to encode my ASP into an encoded form. So after that, I will create a cmdx.asp. So it looked like this. So this is my CMD ASP, a basic, which I can't remember where I copied from. So I just basically created a password on it, and then it will. Yeah. So this is, if you upload this thing to a server, Norton Antivirus will delete it. But if you use a script encoder from Microsoft, it will look something similar to this after encoded. So I will instead upload this into the server. So once I uploaded this, Norton Antivirus won't complain. Okay, so I'm gonna get a nice shell from the web over here. So, but the thing is, when I do like who am I? Who am I? So I will have, I'm only executors of IWAM user. With IWAM user, I will have very little privilege. I probably will not be able to, now this is, there's guest user. I probably will not be able to get a system user. I will not be able to create an administrator or whatsoever. So very limited privilege. So I need to escalate my privilege into a system. So all I need to do, I upload the Norton Antivirus device driver communication privilege escalation into the server, and then which I uploaded here, and then I just run it over here. So when I run this thing, okay, there won't be any output if it is successful. Now when I do a who am I, I'm already a system. So every command that I'm executing right now, I can add new system administrator. So let's say I add a new user. So I probably got successful. If you are a guest, you cannot do all these things. I can even add this thing as a administrator. So if you are a guest, you probably will not get a command completed successfully. So when I do a net user, so I'm going to have the new user created as an admin. Okay, so because I'm a system right now, so like there's like nothing that I cannot do. I can install device driver or whatever. Now this is one of the things that which I think useful for me in this exploit. Now the same exploit can be used in XP. This particular exploit actually detect, because it's a local exploit. Local exploit have a lot of resources that you can use. You can detect whether you're XP or 2000. In this case, I can use a same exploit to attack Windows XP. So it's back 2. So it's back 2. So I am, if I'm currently SK, okay, I do not need any privilege. When I just execute Norton Antivirus, let me start the process so that I can, okay, it started. So Norton Antivirus. So now, by default, if you run this exploit, it will try to escalate all the DLL hosts. If you're escalating DLL hosts, you actually escalate the IIS server. But in this case, I would like him to escalate my shell. Okay, I will just ask him to escalate KMD. Most of you actually, if you're using default install Windows, you're going to have CMD as a shell. But I use my shell KMD. So I'm escalating this KMD. So if this is successful, which of course it will, when I type who am I will obtain a system. So this is still working in XP, so it's back 2. Okay, and basically that will be it. My demonstrations. I will like to open up for question and answer. Thank you very much. Okay. No question? Is there any answer maybe? Because I feel like there's still things that we can do about this. Like maybe some of you would like to share some of your own research. Okay. the jump table. Yeah. Let's take a look at it, the source code itself. Okay. Okay. This is the actual exploit. So now now first, as you can see, I will try to allocate memory in this range because I know we always return 4, so I overwrite part of the second case, and then once I allocate, I will just create a file, and then I call the first device I will control. Now in this case, the out buffer over here will be anywhere in the memory, including in the kernel. So as you can see in the out buffer, okay, no, okay. The actual overwriting will actually be over here in this overwritten with 4. Yeah, this one. This is the actual place where I will the device IO will overwrite with 4. So if you specify the correct memory address to overwrite, you will be able to overwrite the jump address. Now, from what I calculate is, So I'm actually calculating this memory address over here. I will use the get module base to get the base module of Norton antivirus. You'll find this modules over here. This particular function will just obtain the base memory of the device driver, and then this is the base memory of the Norton antivirus, and then I just sum up this thing with this magic number. This is the number which is relative from the actual binary up until this part will be the jump table. So if you calculate the base address with this, total up with this number, you will get the jump table of the half of the first case. So as you can see over here, I will overwrite this memory address with I will put this thing into my buffer. Now this is the buffer where when I send to the device IO later on, it will be overwritten with 4. Okay. Oh, is that okay? All right. Okay. As you can see, you probably will you would like to really take a look at this paper. There's many more information that maybe details that you can find. In fact, this paper also exploiting Norton antivirus on a different offset, different case. Oh, okay. Do we have time for that? I will just quickly try to do it in 10 minutes. So I need to start my soft ice. Organizer, do we really have time? Okay. So, okay. Let's say I do a breakpoint on the device IO. Okay. The optical mouse always have problem with the Norton with the soft ice. Okay. Okay, I'll just set a breakpoint VPX into all the anti-device. Actually, I guess anti-device IO control file. Okay, so as soon as I go back to the user LAN, I got some other process already calling the device IO control. So there is a breakpoint right now. So if you dump the ESP right now, you will see the IO control over here. This is the control code, if I'm not mistaken. I think this is the control code because you can calculate based on the number of parameters. Now we just need to set a control code where the Norton antivirus equal to the code we want. So I will just temporarily disable this. We will only capture the one that interests us, that gives us something interesting. So the code that we want to handle, we want to capture, it's So we want to capture this. Oops, 222A87. So be clear 0. So we need to set BPX, anti-device, IO control, file, if ESP plus, I think this is 618, okay, equal to 0x222, where is that? Alright, A87. A87. Okay. Could you it should be okay. Hey. Oh, okay. We don't need this apparently. Oh, oops. We need this, yep. We don't need this. So I'll just go if the Norton antivirus probably will kick in anytime, especially if you try to scan some stuff. Oh, maybe I got a wrong offset. Okay, I'll just try another tool called strace. Strace the Norton antivirus. Oh. Oh, RTV scan 1328. 1328. The Norton, the soft ice probably just now it didn't kick in, most probably because it's not 18, perhaps it's some other. Let me calculate correctly. 10, it should be 18. Or just before I move into using strace, I still give me one more try. I'll just clear this thing off. BPX, anti-device, IO control file. So yeah, ten. Okay, it's probably 0. That's I think it's going to be 18. How about? Okay. We need to capture the Norton definitely. So anyway, okay. I'll just try this strace over here, see if it's working. Alright, I need to direct this thing into a file. Okay. See if I can get anything here. Okay. So, yep. I find that he's calling anti-device IO with this, and this is 1, 2, 3, 4, 5. Fifth parameter. 5 times 4, 20. 20 is like just 14. It should be 14. Well, let's see. Okay. I'll just try one more time, otherwise maybe I'll try to demonstrate it some other time. Okay. It's not 14, it's not 18, it's like 10, 14, 18. Okay, 1C, how about now? Okay. Okay, need to calculate this. Okay. I think we'll skip this demo. Is that okay? Perhaps I'll try to demo it some other time when I have properly prepared for this thing. Okay. Is that all right? Yeah.
In your opinion, is this exploit available if I use other antivirus products?
Pardon
Or
me?
is this exploit working with other antivirus products?
Yeah, the guy that wrote this paper, he discovered the same problem with the zone alarm the personal firewall, and I believe with you can start tracing. I hope that you guys can start tracing to look for this type of vulnerabilities as well, because as long as he's using neither IO, they are potentially to find something. There's no guarantee, but it's interesting because, like as you can see, even Semantic probably just ignore this problem. He didn't even know that by just using neither IO, attackers can probably utilize the neither IO to override arbitrary memory in the kernel. Yeah, the Microsoft have defined like 4 type of buffer handling: 0, 1, 2, which actually perform all the checking, but he will ignore the third part. He actually leave this thing to the device driver, and if the device driver didn't implement this checking, it will be exploitable. Now, I'm not really sure if there's any conditions of a user process that will be able to specify the output in the kernel. I'm not sure if there's going to be any application that will rely on this trick other than if you want to perform previous escalation. So it's like if they can probably perform a check in the IO XXX to check the output buffer within the user range, which is precisely what they didn't check. That's why this is still possible, and the responsibilities is falling back to the driver developers. If they didn't capture this, which is like not that obvious, it will be the victim of this type of attack. I would suggest if they implement it, I don't think you're going to break any software, because I don't know if there's any user program that would like to have the output in the kernel land. That doesn't make sense. Okay, that is all. Unfortunately, this live tracing thing's not that working well, but I'll try to prepare more for this thing next time. Thank you very much.